Hello everyone and welcome to Lecture 5 for the graduate course ECE 254B, Parallel Processing. I hope you are following the lectures with no problems so far. I would appreciate hearing from you if there are any problems either in the slides that I present or the manner in which I present the material. I'm very open to suggestions for improvements. Please do not hesitate to contact me if you have any ideas. So this is mostly the old chapter 6 in the book, which are called chapter 6A, with a few minor additions. And then chapter 6B and 6C, which will be covered in lecture 6, will deal with implementation aspects of shared memory parallel processors. So in this chapter, we are going to study some a bit more complicated algorithms compared with the simple ones that we studied in lecture 5. So these problems include searching, selection, sorting, and other non-numerical tasks. And in a couple of these instances, we need to talk a little bit about the sequential algorithms, because whereas sequential algorithms for what we saw in the previous lecture are well known to almost everyone, the sequential algorithm for selection, for example, which we cover early on in the lecture, is not well known unless you have taken an algorithms course and have studied it before. So I'm going to spend some time covering the sequential algorithm before we proceed to the parallel version, which is basically a parallelized version of the sequential algorithm. That's why we need to know the sequential algorithm. Okay, so let's get started. The first item of business is dealing with searching algorithms. And the first version of the searching algorithm is when the list is unordered. So if the list is unordered, in order to search it, we basically have, on a sequential computer, we basically have to scan the list looking for the item of interest. If we are lucky, we find the item early in the list, and we basically stop early. If we are unlucky, we go all the way to the end of the list and find it maybe as the last element of the list, or maybe not in the list at all. So that will take order n time, n steps. And on average, we will have to scan half of the list. So the running time, expected running time of the algorithm is n over 2. The worst case is n. Now, parallelizing this algorithm is very simple. In this diagram, I've shown that we have 4 processors. We basically divide the list into 4 equal segments, or almost equal segments, if the length is not divisible by 4, and then have each processor search one of these segments. And then once a processor finds the item of interest, it will report it by storing something in shared memory so that every processor then will know that it was found. If a processor doesn't find the item in the section that it is processing, it will just quit at the end, not storing anything in shared memory, or perhaps store a negative result in shared memory. So this leads to perfect speedup. In other words, if the list has n elements, each of the p processors will get n over p elements, and the expected running time will be roughly n over p. Okay, notice that I didn't say n over 2p, because even though each processor's expected time is n over 2p, because we have to wait for the slowest process, the processor that basically has to scan the entire sublist before it finds the element or gives up. The expected running time is very close to the worst case running time of n over p. Still, n over p is a factor of p over 2 faster than n over 2. Okay, so we have basically linear speedup with p processors. Now consider a sorted list. Okay, sorted lists help for searching because in the sequential case, you are very likely familiar with binary search. So if we have a list of items that are sorted, let's say in numerical order or in alphabetic order, and if you're looking for a particular number or a particular name in this list, the binary search basically goes like this. Look at the middle of the list, okay, the center element of the list, and see if the element that you are looking for, there are three possible outcomes. The element is there, in which case you are done. If it's not there, then the element is either before that or after that element. And because the list is sorted, we know which one. So for example, if you're looking for the number 10 and you look at the middle of the list and you see the number 15, the 10 comes before 15 in an ascending sort. And therefore, we look in the first half of the list. And then we also divide that first half into two equal sections, look at the middle, and so on and so forth. So with each step, with each probe, so to speak, these are known as probes. With each probe into the list, we divide the size of the search space in half, and therefore we need a logarithmic number of steps to complete the binary search. Okay, the parallel version of this algorithm, is called P-array or P plus 1 array search. For one processor, we have binary search. For P processors, we have P plus 1 array search. And the idea is basically, here I've shown the case of two processors, P0 and P1. You divide the list into three equal parts, and then have processor 0 and processor 1 probe the element that is about 1/3 down the list and the one that is about 2/3 down the list. Okay, so P0 probes this element, P1 probes this element. We have two processors, so we divide the list into three parts. That's where the name P plus 1 array comes from. Now, depending on the various outcomes, P0 finds the element we are looking for, in which case we are done. P1 finds the element we are looking for, in which case we are done. P0 determines that the element we are looking for is smaller than this element, comes before in the sorted list, in which case we have divided the search space into 1/3. P1 determines that the element we are looking for comes after this probed element. Again, we have divided the search space into 1/3 its original size. And finally, P0 determines that the element comes after, and P1 determines that the element comes before. Again, we have 1/3, roughly 1/3 of the elements to search. So with two processors, each parallel probe, divides the search space into three parts. More generally, if you have P processors, the search space is divided into P plus 1, uh, the search space size is reduced by a factor of p plus 1, and therefore the number of steps or probes will be log base p plus 1 of n plus 1. We can check this. For binary search, we have one processor, so it will be log base 2 of n plus 1, which is what we know from binary search. Now, log base p plus 1 of n plus 1 can be written as log 2 n plus 1 divided by log 2 p plus 1. This is basically algebraic identity, and therefore we determine that the speed up compared to binary search with one processor is log 2 p plus 1. So roughly log p. Speed up is order log p, which isn't very impressive because we are using p processors and we are achieving a speed up factor of log p. This is optimal in the sense that no comparison-based search algorithm can be faster than this. This can be proven mathematically. So a single search in a sorted list can't be significantly speeded up through parallel processing. But all hope is not lost. Why? Because if the list we are searching in is static, it never changes, then we pay the sorting overhead just once, and then we do a whole bunch of searches and benefit from the speed of searching in a sorted list. However, if our data is dynamic, the sorting overhead becomes significant because each time we add elements or delete elements from the list, we have to resort. And that sorting overhead becomes significant. And therefore, parallel processing can help greatly in speeding up that sorting part, and therefore achieve a greater overall speed up for the search problem, which includes the sorting part, in the case of a dynamic list. And the second thing that saves us is that sometimes we're interested in batch searching. We are not looking for one element, but we are looking for multiple. We want to see whether this list contains the numbers 10, 25, 50, 66, and so on. That's called batch searching. And in batch searching, parallel processing does help, as we will see later. Okay, the next problem we tackle is rank-based selection, or simply selection. What does this mean? We want to find the or a kth smallest element among n elements. Okay, that element, if it's unique, is the kth smallest. In some cases, it's not unique, then one of those kth smallest we are after. For example, suppose this is a list that we have. It has 25 elements, and we are looking for the fifth smallest element. Okay, so there are a whole bunch of the smallest values are ones. 1, 2, 3, 4. There are 4 ones. So the fifth smallest element is not 1. There are a bunch of 2s. 1, 2. And therefore the fifth smallest element is 2. And there are 2 of those, okay? That's why I put an A here. It's not always the kth smallest, but a kth smallest. Okay, so the outcome of choosing the fifth smallest element in this list should be 2. And sometimes we may be interested in the location of that element, in which case this is one location and this is another location. Okay, well, one obvious method to finding the fifth smallest element is to sort this list, say from smallest to largest, and then look into the fifth position of the sorted list, and that's where the fifth smallest element is. But sorting is an order n log n operation as a sequential algorithm. We can't do it faster than order n log n, and that's an overkill because we don't really need the list to be sorted. And in fact, there exists linear time selection algorithms, and one of which I'm going to describe here. Okay, so I'm going to describe a linear time selection algorithm that allows me to find the or a kth smallest element among n elements. So linear time as opposed to order n log n time, which would be required if I try to sort the list. Okay, here's how the algorithm goes. Given a list in which I want to find the kth smallest element, I'm going to use the from now on, assuming that there's a unique kth element. Okay, I divide the list of n elements given to me into the small list of size q. Q is a constant, and later we will determine it to be 5. Okay, but for now, don't worry about what size these sublists are. So these sublists are of size q, so there will be n over q such sublists. Okay, within each of these sublists, find its median. So if q is equal to 5, then find the third smallest, okay, or the third largest, doesn't matter. And because the size of each of these lists is a constant, finding the median of that list takes a constant. Okay, so constant time for each of these lists, and therefore the order of time needed for finding all these medians is n over q. There are n over q such sublists, for each of which we spend a constant amount of time to find its median. So far it's order n over q time. Then we take these medians and put them into this list of size n over q and find the median of this list, median of the smaller list, and call it m. Okay, we can use the same algorithm recursively. The algorithm applied to a list of size n leads to this list, and then we apply the same algorithm to the smaller list to find the median of this list. Okay, and then I'm going to reorganize my list so that all elements that are smaller than this m come in the beginning. All elements that are larger than this m come at the end. And all elements that are equal to this m, so m is a particular value that I know at this point, I determined it. I reorganize the list. Now, I can prove that the larger of these two lists, the one at the top and the one at the bottom, is no larger than 3n over 4. Okay, and therefore no smaller than n over 4. And the reason for this is that this median m is smaller than roughly half of these, is larger than roughly half of these elements, the ones that come before it, if we sorted the list. We are not sorting it, but if we sorted it, roughly half of the list elements come before m. And each of those is larger than q over 2 elements here. And here I'm using some approximations, okay? Because the median is not always really the middle element. If the number of elements is even, for example, it can't be the middle element. But roughly speaking, this m value is larger than half of these, in other words, n over 2q, and each of those elements in turn is larger than q over 2. Therefore, n over 2q times q over 2 will be n over 4. So each of these two lists, up there and down here, has a size at least n over 4, and therefore the larger of the two has a size less than 3n over 4. Okay? And then, because I'm looking at the kth element, I determine the length of this first part. Let's call it L. Let's call this list L. The length is size of L. Let's call this list E. Its length is length of E, size of E. And let's call this one G, and its length is size of G. Okay? Now, if K is less than size of L, then the kth smallest element is bound to be in this part. So basically, I recursively apply my selection algorithm to this list, which has a maximum size 3n over 4. If k is greater than size of L per size of E, size of L per size of E, then the kth smallest element will be in this part, and it will be which element of this part? It will be the k minus size of L minus size of E element. So for example, if there are 10 elements here and there are 5 elements here, and I'm looking for the 20th element, I have to look for the 5th element in this part. So basically, depending on the value of k, I either make a recursive call and do selection in this part, or I make a recursive call and do selection in this part. If neither one of these conditions hold, in other words, k is greater than or equal to L, and also k is less than or equal to L plus E, size of L plus size of E, then one of these elements is the median, and therefore we know that its value is m. Okay, so let's analyze this algorithm to see how much time it takes. So I hope you understood the strategy. The strategy is to find medians in these small lists, put those medians in another list, and find the median of that list. Reorganize the original list so that everything smaller than m comes at the beginning, everything larger than m at the end, and everything equal to m between those two. And then based on the value of k, we have to look in this part for the kth smallest, or in this part, or kth smallest is in this part. In other words, it's equal to m. Okay, so this is basically the sequential algorithm for selection written in pseudocode. Okay, if the list is small enough, then we don't need to apply this divide and conquer algorithm. We just do the selection directly. So this is this part. Otherwise, divide S into S size of S over Q subsequences of size Q. Sort each subsequence. Remember, because each of these small sequences is basically has a short length, we can sort it. Doesn't matter, it will take a constant time to sort. Find its median. Let the size of S over Q medians form the sequence T. The sequence T is basically what I have here in the middle of this diagram. Then find the median of that list T using select recursively. So here I'm defining the select algorithm. Use that algorithm on this T and find its median. Create 3 subsequences, elements of S that are less than m, elements of S that are equal to m, elements of S that are greater than m. Then this is basically what I said in the previous slide. If k is less than or equal to the size of L, then do the selection and list L. Else, if k is greater than the size of L plus size of E, then return M, otherwise return the K minus size of L minus size of E ranked element in this list G. Okay, so it's pretty easy. Now, in terms of time complexity, this is order n time, dividing the list into those parts. Okay, I'm finding their medians, order n time. This one, so if the running time of the algorithm is T of n, this will be T of n over Q because we are applying it to a list of size n over Q. This is T of 3n over 4 because I mentioned that the larger of these two lists is at worst of size 3n over 4. And this part I have to justify why I wrote O of n. But let's assume that it's O of n. With that assumption, this is the recurrence. T of n is equal to T of n over Q plus T of 3n over 4 plus some linear factors, which are called C of n. C is a constant. Okay, it's easy to see that we must have Q greater than or equal to 5 for this recurrence basically to have a linear solution. And if Q is equal to 5, then the solution will be 20 times Cn. I leave this up to you to justify. So it's some linear factor. Of course, 20 is a pretty large constant, and C from the previous slide is at least 2 because this is linear time and this is linear time. Okay, so at least 2n. So theoretically, we have found a linear time selection algorithm whose running time is 20, roughly say 40 times n. Of course, compared with order n log n, for a small list, this may not be better, right? Because this one is 40 times n. The sorting algorithm will be n log n. Depending on the sorting algorithm, there will be some constant in front of it. Let's say it's 10 n log n. So here we have 40 n compared to 10 n log n. So log n must be large enough for this algorithm to make sense, to be more efficient than sorting. Okay, so here's an example that you can study on your own and understand how the various ranked elements of this list of size 25 are found. So the examples used here is to find the 5th smallest element, to find the 9th smallest element, and to find the 13th smallest element. And these are the 3 subcases where the 5th smallest element is in this sublist L. The 9th smallest element is in this sublist, and the 13th smallest element is in this sublist. Notice that the list is not sorted. Okay, you can say it's partially sorted. All the small elements are in this part. All the medium-sized elements are here, and all the large elements are there, but they are not sorted. That's basically the key to why this algorithm can run in linear time. Okay, now back to that question. How do we form these 3 sublists in linear time? Okay, let me go back here. It's pretty easy. So this is the list basically that we are trying to form. We have the original list, which is not, let me go back one more. This is the list I'm trying to form. This is the original list. I can scan this list just once from beginning to end, and I know the value of m at this point. Every time I encounter a value that is less than m, I put it here and increment the pointer. Basically, I start filling this list from the top with elements that are smaller than m. Every time I encounter an element that is larger than m, I put it, the first one I put at the bottom, and then I have a pointer that moves up. So here, here, here. So I start filling the list from the end with larger elements that are larger than m, and from the beginning with elements that are smaller than m. When I finish the list, whatever space is left between these two, so this pointer is now pointing to here, this pointer is pointing to here, I fill those elements with m. I don't even have to fill those elements, because if I ever have the occasion to look into this part, I know that the value is m. I don't really have to look. I just deduce from the value of k that the kth smallest element falls here, in which case I know that it's m. Okay, so this takes basically n steps, because I have to scan the list and transfer each element either to the top of this list or to the bottom of this list. Okay, now let's try to parallelize this algorithm. This is the parallel version of that algorithm with P processors, where P is order n to the power 1 minus x. So this is basically my way of saying that we have fewer than n processors. Okay, how much fewer? This x is the parameter that determines that. So for example, if x is equal to 1/2, then we have square root of n processors. If x is equal to, let's say, 3/4, then we have 4th root of n processors. So we can basically find x for any number of processors that we apply. In particular, if x is equal to 0, we have n processors. However, we will see later that this algorithm, because of the way it's constructed, does not work for x equal to 0. X must be non-zero. Okay, so we must have, in fact, fewer processors than there are elements in the list. This algorithm doesn't work for the case where the number of processors is equal to n. Okay, so some number of processors that is smaller than n, and for example, if n is 1,000, let's say, and you give me 100 processors to work with. So I say 1,000 to what power is equal to 100, and then that gives me the value of x. Okay, so I'm going to describe the algorithm for a general x, not for a specific value of x. Now, if the list is small, then we don't bother to use the parallel algorithm. We just sort S, it's very small, and return the kth smallest element. Otherwise, broadcast the size of S to all P processors. And remember, we have this many processors. Divide S into P subsequences, Sj, of size of S over P. So basically, divide the list evenly among the processors. So each processor will get a chunk of this list, which has this many elements in it. Processor J, all the processors, compute Tj equal to the median of Sj, the list that is given to them, the list that is assigned to them. So we are basically mimicking the sequential algorithm. We divided the list among the processors. Each processor finds the median in the list that it has, by using the select algorithm that we just discussed previously. So we are developing PRAM select, the parallel select algorithm, and we use as part of that algorithm the select, sequential select algorithm that each processor uses to find the median within its sublist. Then once we have found all those medians by the processors, put them into list T. So processor J will put its element into Tj, jth element of T. Then recursively use this algorithm on the smaller list T and find its median using the P processors that we have. So this is the median of the median. So the algorithm follows exactly the sequential strategy, except it's doing it in parallel. Then form the three sublists L, E, and G. You have to now show how this is done in parallel. And then the same thing as before. Look in here, or deduce that the kth smallest element is equal to m. Okay, so this is order n to the x. N to the x is basically how many, if we have p processors and we have n elements, n divided by n to the power 1 minus x is n to the x. That's how many elements each processor gets, and that's basically how much time the select algorithm needs, order n to the x. This is a recursive call. And now each processor determined one median, so the list of size t is equal to p, and therefore this takes this much time, recursively calling the same algorithm. I'm going to show you how these three sublists are formed using amount of time that is equal to the number of elements that each processor holds. And finally, this one is a recursive call to the same algorithm. In the worst case, it takes T of 3n over 4 using P processors. Okay, so the recurrence is T of NP, list of size n with P processor, is this T. That was the first phase, where each processor determined the median and its own sublist. T of 3n over 4p, that's the last part of the algorithm. And C times the number of elements in each processor, that's basically part to be justified. The solution to this recurrence is order n to the x. Therefore, the speed up is theta n, which is basically sequential selection algorithm, divided by this, which is the parallel selection time. And the ratio of these two is omega n to the power 1 minus x, which is omega, the number of processors. Remember, the number of processors is order n to the 1 minus x. And therefore, we have basically linear speedup, which is pretty good. Efficiency is omega 1. The work performed, again, I let you study the justification, is theta n. Therefore, the amount of work performed by the processors is the same as the amount of work used by the sequential algorithm. Okay, what happens? I mentioned that x should not be equal to 1 or 0. Oh, sorry, it shouldn't be 0. It can be 1. If x is equal to 1, then what happens? X equal to 1, the number of processors is basically equal to 1. All right? So that's fine. The algorithm works, and we basically have sequential selection with one processor. What happens if n is equal to 0? If n is equal to 0, then on the surface we see that the running time of this algorithm would be order 1. In other words, the algorithm finishes in constant time regardless of the size of the list. This is unreasonable. It can't do it. And the reason is that in the asymptotic analysis, going back to here, okay, we ignored some logarithmic factors that are basically overshadowed by this O(n) to the x. Now, if n to the x is n to the 0 is constant, then those logarithmic terms, which we ignored, cannot be ignored, and therefore the analysis does not apply. Okay, so let me now finish this part of the discussion by showing you how p-processors can cooperate in rearranging the original list into a list that has all the smaller than m elements at the top, larger than m elements at the bottom, and equal to m elements between those two. Okay, so each processor, once we know what m is, okay, if you go to the algorithm, at this point in step 2, we know what m is before we go into step 3. So we already know what m is. Once we know what m is, each processor basically scans its list of elements and compares them to m. Some of them will be less than m, some of them will be equal to m, and some of them will be greater than m. So it counts those values. So with one scan of the sublist that the processor has, which takes n to the x steps, each processor knows how many elements it has that need to go into this part, how many elements it has that need to go into this part, and how many elements it has that need to go into this part. Let's call them A0, B0, C0 for processor 0, A1, B1, C1 for processor 1, and so on. Okay, so the total number of elements that go into this part will be A0 plus A1 plus A2, and so on. Total number of elements that go into this part will be C0 plus C1 plus C2, and so on. Okay? Now, we can allow these processors to store their values into this part in parallel by doing, so I just show you for this yellow part, elements that are less than m, and the other two will be similar. So this processor knows that it will contribute A0 items to this list. This one knows that it contributes A1 items to that list. This one knows that it contributes A2 items. If I perform a diminished parallel prefix computation on the values A0, A1, A2, what do I get? I get as the first element, first result of that diminished prefix computation, I get 0 here. I get A0 for this processor. I get A0 plus A1 for this processor, and so on. So this processor knows that it should start storing its values that are less than m, beginning at address 0. This one knows that it should start storing its values into this part of the list, beginning at address A0. The result of the diminished prefix computation here is A0. This one is A0 plus A1. So basically, all these processors can store their values into the shared memory in parallel. Of course, they will never conflict with each other because they're storing in different parts of this shared memory. Processor 0 basically will store into the first A0 addresses. Processor 1 begins at address A0, and so on. Okay? So finding A0, B0, and so on takes n over n to the power x step, and then storing these values there also takes, because you store them one at a time, takes n to the x steps. Therefore, the running time for this part of the algorithm is order n to the x, which is how many elements each processor has. All right, so we have designed a selection algorithm that has linear speedup compared to the sequential selection algorithm we discussed previously. Okay. All right. The next thing I'll show you is this algorithm. This is probably the most complicated algorithm we encounter today, in terms of being able to understand it. This is a selection-based sorting algorithm. Because we now have a parallel selection algorithm, basically the strategy for this algorithm is to find a bunch of elements in the sorted list and put them in place. So for example, if I divide the sorted list into 4 parts, let's say this has 20 elements, divided into 4 parts, I find its 5th element, and maybe the 10th element, and the 15th element, and put them in place using my selection algorithm. And then I put all the elements that are less than this M1 into this part of the list, all the elements that are between M1 and M2 here, and so on. And then I separately sort these sections of the list. Okay, because these elements are already in place, and everything that comes before M1 is smaller than M1. For simplicity, let's ignore the possibility that things can be equal. So there may be elements that are equal to M1. We can handle that too, but it's simpler if you ignore that case. So all the elements are different. Therefore, anything that is smaller than M1 comes here. Anything that is larger than M1 and smaller than M2 goes in this part. So once we have rearranged the list so that this property holds, I need to sort these sections separately, and then the entire list will be sorted. Okay, so let's go through the algorithm. Again, if the list is, this is typical of parallel algorithms. When the problem size is small, we just don't bother. We use some sequential sorting algorithms such as quicksort. Okay. Otherwise, we divide the list into k parts. Sorry, yeah, we find k elements of the sorted list. Actually, k minus 1 elements, okay? M1, M2, M3, Mk minus 1. And these elements divide the list into k parts. So our goal is to divide the list into k parts by putting these k minus 1 elements in place in the sorted order, and then moving the other elements in their proper sections of this list, and then sorting each section, okay? So that's the strategy. So for each of these k minus 1 elements, we apply pram select. K is a constant, okay? And the constant happens to be 2 to the power 1 over x. Remember, we had p, number of processors, equal n to the 1 minus x, and k2 is 2 to the power 1 over x. So let's take an example. X equal to 1/2 means we have square root of n processors, and x equal to 1/2, this will be 2 to the 2 or 4. Okay, so the number of segments that we are breaking the list into will be 4 in that case. Anyway, because x is smaller than 1, k will be a fairly small number. If x is, let's say, 1/4, if x is 1/4, this will be n to the 3/4, the number of processors, and this will be 2 to the 4 or 16 segments. Okay, so because k is a constant, we have a constant number of invocation of this PRAM select. And that PRAM select we established takes order n to the power x times the constant k, but we are ignoring constants. So that's the first part of the algorithm. Then for I equals 0 to k minus 1, make the sublist Ti from the elements of S in the range mi to mi plus 1. So this will be the sublist T0. This will be the sublist T1, T2, T3, and Tk minus 1. So make those sublists. And those sublists will be of equal lengths, or roughly equal lengths, because remember, we determined the element that we determined for each of these nj is I times size of S over k. So these are equally spaced, basically, in the sorted list. Now we do 2 steps. So we have k sublists to sort. After we have formed these lists, we have k sublists to sort. It turns out we cannot sort all k sublists at once, and we'll see why in a minute. So we sort half of those sublists in one iteration of this loop, and the other half in this loop. Okay, so we recursively call PRAM selection sort, which is the original algorithm, to solve the first half of these subproblems, and then call that to solve the second half of those subproblems. And as I said, I will explain why we can't do all of them at once. You may say, okay, we have plenty of processors. Why can't we assign processors to these sublists and do all of them at once? We'll see why we can't. So this is the running time for this part. This is the running time for this part. So we have list of size n over k, and we assign to that list 2p over k processors. Okay, now the recurrence will be the time for this sorting the list of size n using p processors. It's 2 times. The reason it's 2 times because we have two parts. First, solve the first half of subproblems, then solve the second half of the subproblems. Plus, everything else in the algorithm was order n to the x or smaller. Okay, and the solution to this recurrence is order n to the x log n. Therefore, the speed up is omega p, efficiency is omega 1, and the work performed is theta n log n. In other words, the algorithm is work efficient, and it also has linear speed up. Therefore, it's efficient in terms of speed up. Again, the same thing applies. We can't set x equal to 1 and use one processor, because if we could set x equal to 1, oh, sorry, x equal 1 is valid. I'm sorry. I made the same mistake before. So this will be x equal to 1 will be n log n, which is basically a single processor used to sort a list of size n. We can't set x equal to 0 because of exactly what I said before, because we are ignoring logarithmic terms compared with order n to the x terms, and therefore if x is 0, we cannot do that. We cannot ignore the logarithmic terms. Okay, now the only thing that remains to be seen is that how do we form these? Again, the same thing that we said before applies, because each processor can independently determine how many elements it will contribute to this sublist by simply scanning. It knows M1, so everything that is smaller than M1 will go here. It knows M2, so everything between those two. So each processor independently determines how many elements it will contribute these sublists, and then we perform parallel prefix computations to determine where each processor should start storing its values. This example, I'm going to let you study on your own to see how the algorithm actually works on this pretty short list to be stored. Okay, so this algorithm is theoretically satisfying because it's optimal in a theoretical sense. However, in doing the complexity analysis, we have no idea what C is. And so basically, even though it's order n to the x log n, there may be a large constant in front of here. Furthermore, the algorithm, developing the algorithm, is fairly complicated and error prone. There are, fortunately, alternative sorting algorithms that are not optimal in the worst case, but they have pretty good average case. And we basically use these in practice. And I'll give you a few examples of such algorithms. So this one is called sample sort, or sorting via random sampling. Okay, we assume that the number of processors is much less than square root of n, and this is a reasonable assumption. When we sort huge lists, let's say 1 million items in the list, or maybe even more, square root of 1 million is 1,000, and if we have far fewer than 1,000 processors, then this algorithm works well. So given a large list S of inputs, a random sample of the elements can be used to find the K comparison threshold. One reason this algorithm was complicated is we insisted to find these elements that are equally spaced in the sorted list, and that led to using these selection algorithms and doing a lot of work. Okay, so this algorithm proceeds like that, like this, which I explained. So processor J picks this many random samples of this many elements that are assigned to it, and it stores them in its corresponding section of a list T of length S over P. So we basically extract, okay, this many random samples per processor. So the total number of random samples will be size of S divided by P. Multiply this by P. Okay, so we find this list that is smaller than the original list. It is formed from random samples extracted from the original list. Now this list T is small enough for us to sort it using just one processor. Processor 0 sorts this list, which is much smaller by a factor of P than the original list. Okay, and the comparison thresholds are picked from this sorted list. Okay, processor J stores its elements falling between mi plus 1 into Ti, and processor J sorts the sublist Ti. So what we have done here, we have found these elements instead of through selection so that they're guaranteed to be equally spaced from random sampling. So if we are unlucky, the sizes of these sublists will be quite different, okay? And therefore the work, each processor will sort one sublist, use sequential sorting, but one processor may have a shorter list, another one may have a longer list. But on average, this will not happen. It's very unlikely for this to happen. And therefore, the performance of this algorithm on average will be very close to n log n over p. N log n is the sequential sorting time, and p is the number of processors. And therefore, it's fairly efficient. It's fairly easy to code because basically we have very simple steps. This is a sequential sort over here. These are sequential sorts performed individually by processors. And this sampling is pretty easy to do, okay? So this is sorting through random sampling, or sometimes it's called sample sort. This is bin sort or bucket sort, which is similar to random sort. Suppose our input values are in the range 0 to m. In other words, we know values. So for example, if the numbers are to be sorted are 16-bit numbers, then we know the range of those numbers. Okay? Divide the range into p subranges. And these subranges are 0 to m over p, n over p to 2m over p, and so on. Now, we basically divide the elements. So given this list, we scan the list and put the elements into buckets or bins. So for this example, I've chosen the bucket. So numbers go from 0 to 49. So one bucket contains numbers 0 through 9, another one 10 through 19, and so on. So 29, I put it in this bucket. 25, I put it in this bucket. 3 goes in this bucket. Okay, so one scan of the list allows me to put numbers in the various buckets. And then I sort each bucket independently because all the numbers in this bucket are smaller than numbers in this bucket, in turn smaller than numbers. So if I sort the buckets independently, my entire list will be sorted. So sort this bucket, 3, 9. This one doesn't have anything. 21, 25, 29, 37, 43, 49, and my numbers have been sorted. Again, notice that, so for example, if the buckets correspond to processors, and I have 6 processors, one processor may get more work than another processor. But on average, it's unlikely for the imbalance to be very serious. In fact, if it is serious, then we have a worst case situation, but the average case basically is pretty good. So average time is order n over p, where the processors go and put their values into the buckets, plus order n over p log n over p. This is basically the sorting time for each bucket, which is done by one processor. Now, if the range of values is fairly small, this becomes even more efficient. Because, for example, suppose I have numbers 0 to 9, a list that consists of numbers 0 to 9 only, nothing else. Then basically I scan the list and I have 10 counters corresponding to values 0 through 9. Whenever I encounter 0, I increment the counter for 0. If I encounter 1, I increment the counter for 1. And by the time I get to the end of the list, I know how many of each of those elements I had, and therefore forming the sorted list is a trivial matter. So this will be basically linear time. So if m is a fairly small constant, then this bucket list, basically, I don't have to put stuff in the buckets. I just use a counter to keep track of how many of each of these elements I've encountered so far. And then at the end, I basically form the sorted list by using those counters. If I had, let's say, 5 zeros, I put 5 zeros in the list. If I had 11 ones, then I put 11 ones. So this will be linear time, okay? That's a special case of bin sort or bucket sort. Okay, the last sorting algorithm I describe is radix sort. So what is radix sort? So radix sort is general. You can do it in any radix. Basically, binary sort is when the radix is equal to 2. So I've shown an example here. Suppose I have k-bit keys. So for example, these are the numbers I want to sort, the keys I want to sort. And in binary, these keys have these representations, the binary forms. Okay, I sort these numbers by the least significant bit. So least significant bit of 5 in binary is 1, 7 is 1, and so on. And I put all the ones that have least significant bit equal to 0 at the top, and all the ones that have least significant bit equal to 1 at the bottom, maintaining the order. This is a key requirement. In other words, the first item that has least significant bit equal to 0 should go there. The second item that has least significant bit equal to 0 should go there, and so on. So the order must be maintained. Similarly for 1, the first item that has least significant bit equal to 1, and so on. Then sort by the middle bit. Okay, the middle bit is 0, 0, 0. Sorry, I'm sorry. I have to look at this. 0, 0, 0. There are 3 of them. So I move them up there. Again, maintaining the original order. And then the middle bit is equal to 1 for this, this, and this. And finally, sort by the most significant bit. Again, most significant bit equal to 0. This one, this one, this one, and this one. There are 4 of them. I shift them to the top. And at this point, the list has already been sorted. Okay? So if I can do these steps of sorting by least significant bit, by middle bit, by most significant bit efficiently, if this is efficient, then I need k such steps to sort the entire list. And if k is a constant, let's say I'm dealing with 16-bit numbers, so k is 16, I need 16 such steps. Okay, so how much time do I need for this step? To do those steps in parallel, it turns out that I need log n. Okay, so the running time of this algorithm, it requires k steps. Each step takes log n, so it will be k log n. And if k is a small constant, it will be order log n, which is pretty good because I reduce the running time from n log n to order log n. And this is very good speed up. Okay, so why is it that I can do each of those steps in logarithmic time? Okay, so I'm going to show you the first of those steps that I had before, basically sorting by the least significant bit in log n steps. All right, so here I have the bit zeros. I form the complement of bit 0. This will be constant time. I'm assuming I have as many processors as there are elements here. So form the complement of bit 0 in constant time. Perform a diminished prefix sum on these complements. So the diminished prefix sum is 0, 0, 0, 0, 0. It's diminished, remember. I just add the previous. 1, 1, 2. And then I ignore the values that sit next to 0. So I'm only concerned with values that sit next to 1s. Remember, these 1s really zeros in the original data. Okay? So basically, this is the first 0, the 0th 0. This is the first 0. This is the second 0. And therefore, this diminished parallel prefix computation tells me the location of these three elements in the list that is sorted according to the least significant bit. So this is element 0, this is element 1, this is element 2. Here they are. Element 0, element 1, element 2. And then I repeat the same thing with doing a prefix sum on 0, and then adding this 2 to the result. This 2 basically says how many elements of this list are occupied by these zeros, the elements that are zeros and least significantly. So prefix sum is 1, 2, 3, 4, 4, 4, 5. Again, I'm not interested in these values, only the ones that correspond to 1s. And then I add 2 to this, and these will be the locations of those elements that have least significant bit equal to 1 in this rearranged list. So element 0, element 1, element 2, element 3, 4, 5, 6, 7. And once I know those locations, each processor has determined the location where its element should go in the rearranged list. It will just simply copy the element into that location. So I needed 2 prefix sums, one diminished prefix sum and one regular prefix sum. And each of these we know takes logarithmic time, and therefore the total time for this step is logarithmic. So there will be k logarithmic steps. Okay, the last problem that I will discuss fairly briefly is an example of geometric problems, so that you have seen at least one example of this, is finding, and I'll discuss the solution very briefly. I won't go into the details of the algorithm, but just the strategy for solving this problem. Okay, so suppose you have a bunch of points in the 2D space, x and y coordinates, and you want to find the convex hull of this point set. Convex hull is the smallest convex polygon that encloses all of these points. And we as human beings, just looking at these points, and we are very easily able to determine what the convex hull is. Those are basically the points that are, furthest out, let's say, in this point set. So how do we go about in writing an algorithm for the convex hull problem? Well, first let's examine some properties of, so why is it that, oh, by the way, the convex hull is characterized by the set of points in some order. Let's say the output of this algorithm will be 1, 7, 11, 15, 14, 8, 2, 0. Okay? The set of points on this exterior or convex polygon in some order. So that's the expected output of the algorithm. Okay, so why am I certain that 1, 7, for example, this line, is part of the convex hull, whereas this line is not? Well, it's very easy. This line is part of the convex hull if all the points fall on one side of it. 1,7 is part of the convex hull because all the other points fall on one side. This line is not part of the convex hull because there are points on both sides of it. Okay, so this is a simple property of convex hull. Another property is that if you draw this line that belongs to the convex hull and draw from this point to another point, let's say to point 11, this angle is always in the same direction. So for example, if this direction is positive, all these angles will be positive. So all points fall on one side of that line, and all these angles are basically have the same sign. These are basically the same property. So here is a PRAM convex hull algorithm described in a very high-level terms. Given the points, sort them by their x coordinate. We already know how to sort things. So sort all these points by the x coordinates, and then divide the resulting sorted list into square root of p subset. P is the number of processors. So if you have p processors, let's say 16 processors, then divide these into 4 subsets. Okay, each subset will have 4 points. Okay, I'm assuming n is divisible by square root of p for simplicity. It doesn't matter if the size of these sets is not exactly equal. Okay, then here I have square root of p points in this subset, square root of p points here, square root of p. Then use square root of p processors to find the convex hull of these square root of p points. Square root of p processors to find the convex hull of these p points, and so on. Okay, then we now have to combine these small or subset convex hulls, and combining them basically involves drawing tangent lines from points in this subset to points in that subset. So for example, this tangent line will be part of the larger convex hull, whereas let's say this tangent line will not be. So the algorithm basically tries to find out which of these tangent lines will be part of the convex hull. So this tangent line, then from here to here. And on the bottom side, this. No tangent line to these points will be part of the convex hull, but this tangent line will be. Okay, so the convex hull will be this, 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 this line, this one, and this one. Okay, so analysis of the algorithm is the convex hull time for p points with p processors is convex hull time for square root of p points with square root of p processors plus c log p. So basically the gist of this algorithm is that those combining operations can be done in order log p time using p processors. And the solution to this recurrence is 2c log p, so order log p. Okay, so basically this is illustrating what happens if these are convex hull, adjacent convex hull in those subsets. If this happens, if this tangent line and this tangent line have such an angle, then this convex hull will not contribute any point to the overall convex hull. On the other hand, if the tangent line from this hull these two takes this form, then all the lines and points between A and B will be part of the convex hull. So this line and this line, or points A, B, and whatever this is called, will be part of the convex hull. Okay, so I'm going to skip those details, but I just wanted to leave you with some idea of how these geometric problems are solved. And we can often find pretty efficient algorithms for solving such problems on the PRAM model. Okay, so this is all I wanted to say regarding chapter 6a in the textbook. And next time, next lecture, lecture 6, I will cover chapter 6b and 6c. There are a lot of material in those two chapters, and these are basically more or less new chapters, but I'm going to skip some topics in order to fit all of the material into one lecture. Okay, take care and stay safe until we meet again in lecture number 6. Bye for now.